So in this video, we are going to be introducing some notation so that we can generalize the discussion of ODEs that we had last time in terms of classification to a system of ordinary differential equations. After this, we are going to be looking at a number of familiar ordinary differential equations in the scalar form first, and then we will extend that in the vector form so that we can look at systems of ordinary differential equations. After we are done with this, we will look at some more familiar ordinary differential equations, including some systems, including some nonlinear equations which arise in familiar science and engineering applications, and these would be examples of what we can call celebrated ODEs. So let's recall that we are interested in describing how a dependent variable y, which depends on a single independent variable t, evolves in some dynamical problem. And so here y is a scalar variable, it's a single value, and we are assuming that y takes on real numbers, so y belongs to the set of real numbers. The notation that we have used previously was to write the time derivative of y as dy dt. We will also introduce a shorthand for dy dt. We will use a shorthand by putting a dot on top of y, or y dot, which is a shorthand for the time derivative. In many books, the notation of putting a prime on top of y, or y prime, is also used to denote the rate of change of y with time. So we will use the shorthand as we proceed. So let's now extend this to the case where the dependent variable is not a scalar but is a vector valued quantity which has m components. So we will denote such a dependent variable by a boldface big Y as written over here. It's a function of time, and these are the m components that it has. In different physical applications, these components will have different meaning, which we will see in particular contexts later on. So remember that this big Y with boldface is a vector with m components, and so if we want to represent the time derivative of this vector valued quantity y, we can put a dot on top to write in shorthand form the rate of change of y, and its various components have been displayed here, dy1 dt all the way up to the mth component dym dt as shown in form of this vector. So we're going to be using this notation for writing systems of ODEs as we proceed. Okay, so let's discuss some ordinary differential equations that may be very familiar to you from the past. And so let's look at the simplest differential equation. Y dot equals minus alpha times y. Y is a scalar dependent variable. We can classify this equation using properties that we described in the last video. I will describe it as a first order, linear, homogeneous, and autonomous differential equation. This equation arises in context of population dynamics, in chemical kinetics, and in radioactive decay. Radioactive decay you might remember from your high school physics, and so let's go back to the equation. Y dot equals minus alpha times y. Y is the amount of some radioactive species that may be present. Its rate of change in time is proportional to the amount of radioactive species that is present times the time constant, and this minus sign ensures that its evolution in time corresponds to a decay, and the solution to that is an exponential solution that may be familiar to you. Later we will consider more specific examples for particular applications which generalize on this idea. Extending what we have done to the vector form, where y is m component vector, its rate of change is given by the right hand side, which corresponds to a matrix. A is a matrix, m by m matrix, times m component vector y. So the result of this matrix vector product is a vector of size m, and so that's equal to the rate of change of y. So in general, the matrix M could be a function of the solution that we seek, a y, capital Y of t, and so in general this is a nonlinear system of m coupled first order ordinary differential equations. Such systems commonly arise in the context of chemical kinetics and in the context of population dynamics. For example, if you think about the way a particular fuel might burn, a fuel has many components, many chemicals, and they interact with other chemical species, and so rate of progress of the chemical reaction depends on the concentrations of all the participating species, and to represent this dependence, one needs to express the rate of reaction in terms of all of the constituent components, and since reaction rates depend on concentrations of multiple elements, one needs to represent it in terms of a matrix here. Likewise, for population dynamic studies, if you think about the population involving multiple species, one species may be a predator species, other species may be a prey species, or there may be multiple prey species. Their interaction requires representation in terms of a system of equations. Moving to a second order differential equation, this is again a familiar second order differential equation to you, I'm sure. Y is a scalar dependent variable, my double dot plus cy dot plus ky equals some forcing f of t on the right hand side. We can think about m as a mass, c as a resistance or damping, and k as a spring that is involved in this equation. This is according to the classification that we discussed previously. This would be a second order linear inhomogeneous because we have a right hand side present, and non-autonomous because this right hand side is a function of time. Such an equation arises in context of vibrations and oscillations. These vibrations and oscillations could be vibrations and oscillations of mechanical systems, which we can think in terms of mass, spring, and damping, or it may be associated with electrical system where we may be thinking about a rate of change of some charge. Q is the charge, is a rate of change in time, two time derivatives. This is the inductance, L, this is the resistance, big R, and C is the capacitance in a circuit that's driven by some externally applied electrical voltage, E, which is on the right hand side of that equation. So hopefully these are familiar equations and will remind you of certain properties of these, but the next step is to generalize the second order system of equations to a system of second order equations. So generalizing this discussion, let's consider a system of second order coupled differential equations for a dependent variable which is m component vector, capital Y. Capital M, capital C, and capital K now are m by m matrices that can be interpreted as mass, damping, and stiffness matrices. Familiar left hand side here, my double dot cy dot plus ky equals some forcing F, which is a vector valued forcing on the right hand side. So problems like this are natural in studies of vibrations and oscillations in mechanical systems, in electrical systems, in acoustic systems, or in systems that involve coupling between elements of systems that are driven mechanically or electrically and may produce an acoustic response, or system may be driven electrically and produces a mechanical response, or any other way that you can imagine. And depending on whether these matrices are constants, if they are constants, then this would be a linear system. If these matrices are allowed to depend on the dependent variable y itself, then these would become nonlinear, second order coupled systems of differential equations.